How to measure the ionospheric composition with the Global Navigation Satellite Systems, or GNSS. Most of you would say, but why do we need to know anything about the ionosphere? There are two very good reasons why we do. Firstly, because it's the medium where long-distance radio communication takes place, and secondly, because it's very important for the navigation systems that rely on radio transmission. It all started in the beginning of the 20th century with the radio. In 1901, the Italian Guglielmo Marconi initiated the first transatlantic radio transmission. Little did he know that this was only possible because of an yet unknown layer in the atmosphere. The scientists back then knew only basic things about the atmosphere. A close look at its structure shows that 99% of its mass is found in the bottom 30 kilometers, and above 1,000 kilometers we could not distinguish it from the interplanetary medium. The ionosphere is that part of the atmosphere where free electrons and ions are present in high concentrations. It is situated between 60 and 500 kilometers above the Earth's surface. But this was unknown until 1925, when the height of the ionosphere was measured for the first time. Appleton and Burnett proved that the signal between the continents traveled not directly between the radio masts, but was reflected by the ionosphere like from a mirror. Let's see how the ions are formed, using as an example the nitrogen atom. Nitrogen is actually the most abundant gas in the atmosphere. Like all atoms, it has a nucleus and a cloud of electrons circling around it. The nucleus is positively charged, and the cloud of electrons is negatively charged. An electron can be split from the cloud by a collision with high-energy particles coming from the Sun. This is why the ionosphere changes on a daily basis. During the night, when the Sun is not present in the sky, there is only one mirror, the F layer of the ionosphere. With the sunrise, two more layers appear in the sky. These are the E and D layers. And all these layers, or mirrors, are different because they contain different concentration of free electrons and are situated in different altitudes. While the D layer is the lowest one, the F layer is the highest and contains maximum concentration of free electrons in the ionosphere. Now, the reflection or passing through an ionospheric layer of a radio signal depends on the layer's concentration and the frequency of the signal. At lower electron densities, the radio signal is permitted to pass, but when the electrons exceed a critical number, the layer starts to act as a barrier. The frequency dependence of the layer allows the building of the basic instrument for ionospheric research during the 20th century, called Ionosonde. It works on the principle of sending successive pulses of radio waves from 2 to 20 MHz up into the ionosphere. These pulses are reflected at different layers, and their echoes are received and analyzed by the control center. For satellite communication, we need frequencies which will penetrate the ionosphere indifferent to its concentration. This is why Global Navigation Satellite Systems, or GNSS, use signals with 1,000 times higher frequency than ionosondes. But still, the ionosphere bends and disturbs the signals. These disturbances influence the position determination by reducing its precision up to several kilometers. And here is the clever bit. The GNSS, instead of using one frequency, uses two. Each of the frequencies is altered by the ionosphere on its way to the surface of the Earth. But if we find the difference between the signals when they arrive, we can estimate the state of the ionosphere above our receivers. This will provide us with not only better positioning, but also with data about the state of the ionosphere at any particular moment across the entire globe.